A very good morning to all of you. I cordially welcome you all for this engineering thermodynamics course. And today's classroom discussion topic is entropy change mechanism and entropy generation in open and closed systems. And the motivation behind these particular topics is it is very essential to determine the entropy change in various processes and entropy change mechanism and to know its applications in daily life. And the outcome of this lecture is at the end of the lecture, you should be able to discuss entropy change mechanism and entropy generation in open and closed systems. So, because we studied that entropy, it is a measure of molecular disorderness or the molecular randomness. So, the disorderness and randomness is closely associated with the entropy concept. So, whenever a system becomes more disordered, then automatically the position of the molecules also will become less predictable and automatically the entropy value will be increases. And whenever we are having the solid phase as well as the gaseous phase, so in which case the entropy of a substance is lower and higher. So to answer that particular one, so the entropy of a substance is lowest one in the solid phase and highest one in the gaseous phase because due to the molecular disorderness of the molecules. And we already studied that whenever we are having any irreversible process, so the entropy of the universe always will increases because whenever you are heating a particular working fluid or heating a gaseous element and whenever you are opening this particular the stopcock, automatically the molecules are will become the more movement will be taking place. So just you are able to see that is the more orderness of the molecules as well as the disorderness of the molecules. So whenever the disorderness is increases, automatically the entropy also will be increases. So now how can we find out the change in entropy of the universe? And that is nothing but the entropy of the system plus entropy of the surroundings always should be greater than or equivalent to 0, and it should be greater than 0 for an irreversible process and it should be equivalent to 0 for a reversible process, and whenever it is less than 0 it is violating the second law of thermodynamics, it is impossible. So entropy transfer mechanism, that is how the entropy transfer mechanism is taking place. So just you see here, because here the surroundings are basically kept at the T0 temperature. So it is the T0 temperature and here it is the system. So system and surroundings are separated by means of a boundary. So the heat transfer is taking place like this. So you know that the entropy formula, it is nothing but ds is equivalent to delta Q reversible by T, because whenever I am keeping the equivalent sign, so he definitely here I have to write down the reversible. So ds is equivalent to delta Q reversible, that is a reversible adiabatic, by T. So ds surroundings, because the surrounding temperature, because here the system temperature is T and the surrounding temperature is T naught. So ds surroundings is nothing but Q by is a T naught. So ds system, because here the heat transfer from the system is taking place. Heat transfer from the system is taking place. So that's why it is minus sign I am keeping here. So minus Q by T naught, because here also we are assuming that the system is at T naught temperature. So like this, now we can find out there is no entropy transfer along with the work transfer. So that is the one of the example here I have shown you. So entropy change, it is always equivalent to the entropy transfer plus entropy generation. That is ds system is always equivalent to ds of entropy transfer plus ds of generation. So we are able to find out, so from this particular the equation, that is the entropy generation according to this particular equation, that is the delta Q by T. According to the reversible process, it is equivalent to delta Q by T irreversible process plus PdV minus delta W by T. So that is this is the equation, that is we can see that is the system 122 is taking place here, that is the work transfer is taking place and the heat transfer is taking place. So how can we find out the entropy transfer? So that is from the first law of thermodynamics we studied that dE is equivalent to delta Q minus delta W, and here we can find out the delta Q is equivalent to dE plus delta W. And dE is nothing but whenever you are integrating from 1 to 2, we are able to get E2 minus E1 plus W12. And from the second law of thermodynamics, we studied that entropy principle says that entropy of the universe always increases, it never decreases. So that's why S2 minus S1 value should be always greater than or equivalent to delta Q by T. So from that particular one, we can write down S2 minus S1. So whenever you are taking this particular delta Q by T here, so minus delta Q by T, that will be equivalent to S generation. So S generation value should be always greater than or equivalent to 0. So that's why the second law states that in general, any thermodynamic process is accompanied by entropy generation. So entropy generation is must whenever there is a process is taking place. The same thing I have illustrated through this particular diagram. That is, there is a 1 to 2 is a reversible process is taking place, and here there are two irreversible processes are taking place according to is a path A and path B. So how can we find out the entropy generation here? So that is here you can compare. So S generation A is always greater than S generation B. So what is the reason means? The path A is more irreversible than path B and involves more lost work, because the more amount of the work is lost during this particular the path A. So that's why the whenever there is a lost work, whenever there are more irreversibilities are taking place, or whenever there are more irreversibilities are presented within the system, and whenever there is more amount of the work is lost, so automatically the entropy of that particular the system or the body will be more as compared to the remaining body. So based on this particular concept, we can say that the entropy generation within the body A always it is greater than entropy generation within the body B. So like that we are able to give the equations for the entropy generation. So now it is the entropy generation in the open system, because we studied that open system is nothing but is a control volume, and whenever we are having the control mass, that leads to the closed system as well as the isolated system. So because it is pertaining to the open system, so there is a mass transfer will takes place as well as energy transfer also will takes place. That is the meaning of the open system. So the same thing you are able to observe here. So the mass inlet and mass outlet, it is the inlet and exit. So mass transfer taking place as well as the energy transfer is also taking place within this particular the system. So by this particular steady flow energy equation, because in the first unit we studied about the steady flow energy equation as well as the continuity equation. So just you apply this particular the concept to the steady flow energy equation, the 7.33 and 7.34 will give you the information about the entropy generation in and the open system. So similarly, it is once again, it is further reduced to this particular equation. That is, it is only substituting in the steady flow energy equation. So we are able to derive the entropy generation in the open systems as well as the closed systems. So this is a important one, because whenever there is a entropy change mechanism is taking place, automatically the entropy generation definitely it will happen. So we have to find out the entropy change in the open system as well as in the closed system. That is only just it is substituting in the steady flow energy equation concept. I hope you understood this particular concept, and we will meet you once again in the next topic of the classroom discussion. Thank you one and all for attending and listening this lecture.